Hello and welcome to this video. In this video, I'm going to take you through the process of deriving Newton's second law of motion. Newton's second law of motion. Before we do that, there is one particular concept that I'd like you to bear in mind, and this concept is about resultant force. I'd like you to understand or to remember that if you're given an object and this object is acted upon by several forces, like for example, these are force of 40 newtons, maybe to the right, and there is a force of 30 newtons to the left. I'd like you to understand that the resultant force is 10 newtons to the right. This is the resultant force. You could have a situation where there are two forces or more than two forces, and the situation is such that if one is 40 newtons, the other one is in the opposite direction of 40 newtons, the resultant force is 0. You could also have a situation whereby the two forces are acting in the same direction, where you have a force of 30 newtons acting on that object to the right, and a force of 40 newtons acting on that body to the right. The resultant force is 70 newtons in that direction. So the idea of resultant force is very important in this law, because we are going to mention resultant force. A resultant force is that single force which is the sum of all the forces which are acting on this body. For example, the sum of 40 newtons and 30 newtons, when they are acting in opposite directions, will be 10 newtons in the direction of the 40 newton force. If we have two forces of equal magnitude acting in opposite directions, then the resultant force is 0. By resultant force being 0, it does not mean that there is no force acting on the body. Like, for example, in this case, there are two forces acting on that body, but the resultant force is 0. If the two forces are acting in the same direction, then it is very easy. You just need to add the two forces and you get the resultant force. So your ability to determine the resultant force which is acting on a body is important in this particular law. The other concept that I'd like you to remember is the concept of momentum. Momentum of an object. The momentum of an object is the product of its mass and its velocity. So once you get the mass of the object, multiply by its velocity, you're going to get a physical quantity which we refer to as momentum. The symbol that we use for momentum is P. So we can say P is going to be equal to mv. Momentum has SI units, and these SI units can be derived. And you can see that the SI unit of momentum is the SI unit of mass, which is kilograms, and the SI unit of velocity, which is meters per second. So the SI unit of momentum is kilograms meter per second, or Newton seconds. We are going to see in this video that kilograms meter per second is the same as Newton seconds. But for now, I've been able to show you that how the SI units of momentum are derived. I simply need to get the SI units of mass multiplied by the SI units of velocity, and I get the SI units of momentum. It's just that simple. Momentum is a vector. And a vector is a physical quantity which has got both direction and magnitude. The direction of momentum is the same as the direction of the velocity of the object. For example, if you're given an object here, an object of 2 kilograms moving to the right with a speed of 5 meters per second, then the momentum of this object is 2 kilograms times 5 meters per second, and you are going to find that it is 10 Newton seconds to the right, or 10 kilograms meter per second to the right. If that object is moving to the left, the same object of mass 2 kilograms moving to the left with the same speed of 5 meters per second, then we're going to say that the momentum of this object is going to be 10 Newton seconds, this time to the left. These two momenta, they are not the same. Although their magnitude is the same, 10 Newton seconds, their directions, you can see that their directions are different. And by the fact that their directions are different, the two momenta are not the same. They are not the same. They are different. So momentum is a vector, and if you want to get the direction of that momentum, the direction of the momentum is the same as the direction of the velocity. Like you can see here, the momentum of this object is 10 Newton seconds to the right because the object is moving to the right. The momentum of this object is 10 Newton seconds to the left because the velocity is towards the left. Understand that. So the definition of momentum and the fact that it is a vector quantity. Remember, this one defines momentum. Momentum is a physical quantity, and it is defined as the product of the mass of the object and its velocity. When we look at this equation, of course, we can be able to tell that factors which affect momentum of an object are the mass of the object and the velocity. The mass of the object and the velocity. If you want to increase the momentum of an object, you can either increase its mass, which is not very easy, although you can add masses onto a given mass. Like for example, if we put a mass here, then we are going to increase the mass of that particular object. But the easiest way to increase the momentum of a given object without changing its mass is to change the magnitude of its velocity. These are the two factors which affect momentum of an object. Momentum of an object can also be zero if it is stationary. If it's stationary, we are multiplying that mass by 0, which will give us 0. So those are the basics about momentum. Now let's go to a given situation here. Suppose we have an object of mass m. And at a certain instant of time, it's moving in this direction with an initial velocity u. Suppose a resultant force F, we have already referred to this resultant force. We have seen how we can get the resultant force acting on an object, so that one is not a problem. We have an object of mass m. It's moving with an initial velocity u, and then we have a resultant force F acting on it for time t in such a way that after time t it has increased its velocity to v. So we have an object of mass m moving with a velocity u, then a resultant force F acts on that object for time t, increasing its velocity from u to v, where v is greater than u. And again, you know the effect of a force on an object. We have already talked about effect of forces on objects, and one of them is that it can make an object which is already moving to increase, to accelerate, that is to move faster and faster. This is such a situation. A resultant force F acts on it for time t, increasing its velocity from u to v. In other words, the object has accelerated. Let's see how we can calculate certain physical quantities related to the momentum of this object. We can determine its initial momentum, pi. The momentum it has here initially will be equal to its mass times its initial velocity. We can get its final velocity. After time t, its final velocity will be equal to its mass times the final velocity. And we can see that this momentum has changed. We can get the change in momentum, which we are going to call delta P. Delta P is going to be equal to final momentum minus the initial momentum, and this one is going to be equal to mv minus mu. We can factor out m, in which case we are going to get v minus u, and this will be the change in velocity. If we multiply the mass of that object by its change in velocity, we are going to get a physical quantity which we refer to as change in momentum. Change in momentum. We are not going to stop at that point. We are going to find the rate of change of momentum. Rate of change of momentum, which is change in momentum divided by time. In other words, the change in momentum per unit time. Remember, it had an initial velocity mu. Now it has, after time t, it has a final momentum mv. We can get the change in momentum per unit time. And this one will be equal to change in momentum. We have seen that it is equal to mv minus u. We divide all this by t. And you will agree with me from kinematics, v minus u over t is acceleration. And therefore, the rate of change of momentum of this object is equal to mass times its acceleration. It's at this point that we would like to introduce Newton's second law of motion, because it gives us the relationship between the force which has caused this rate of change of momentum. And Newton's second law of motion states that this rate of change of momentum, ma, is directly proportional to the resultant external force acting on that object. The rate of change of momentum of the object is directly proportional to the resultant external force acting on that object, and that rate of change of momentum acts or is in the same direction as the resultant force. So we can say that m a times a certain constant k is going to be equal to F. If F is in newtons, m in kilograms, a in meters per second squared, then the value of k is found to be equal to 1. And it is at this point that we get F is equal to ma. This is the mathematical statement of Newton's second law of motion. Remember, if you are asked to state Newton's second law of motion, you should state it in words. The rate of change of momentum of an object is directly proportional to the resultant external force acting on that object, and it takes place in the direction of the force. And then you go on to write down this, and then you say this is the mathematical statement of Newton's second law of motion. And this is how we derive the mathematical statement of Newton's second law of motion. Remember, the rate of change of momentum of an object is directly proportional to the resultant external force acting on that object, and the rate of change of momentum, it takes place in the direction of the force. In other words, the rate of change of momentum is in the direction of the force. Let's see some of the facts which we can get from this statement. When we write this statement that F is equal to ma, there are a few things that we need to understand. Remember, F is a resultant force. This is the mass of that object on which this resultant force is acting, and this is the acceleration which is produced by this resultant force. It's very important to understand this, that you've got an object of mass m, and then there is a resultant force acting on it. Its value is F. The effect of this resultant force on this object is to make the object to accelerate in the direction of the force. This acceleration will be in the direction of the force. It is so important to realize this. Number one, that there is this force which is a resultant force which acts on this object, and then it produces an acceleration on that object, and that acceleration must be in the direction of the resultant force. Very important. So when we come to this equation here and we put arrows like this, it is to show that this resultant force is a vector, the acceleration is a vector, and that this acceleration is produced by the resultant force. So what stems out of this is that if we see an object accelerating, then it is proof that there is a resultant force acting on it. Remember that, very important. If you see an object which is accelerating in a certain direction, then it means there is a resultant force which is acting on it in that direction. Similarly, if a resultant force acts on an object, its effect is to produce an acceleration on that object. If a resultant force acts on an object, its effect is to produce an acceleration, and this acceleration must be in the direction of the resultant force. Very important. These points are so important if you are interested in solving problems which are related to Newton's second law of motion. You must understand these concepts. Let's go ahead and break down this law, work backwards. We have seen that A is V minus U over T. We can multiply both sides by T, and we get Ft is going to be equal to mv minus u. Remember, the right hand side, we called it change in momentum. It's the mass of the object multiplied by the change in velocity. We get change in momentum. The left hand side is a product of the force and the time for which that force is acting, and it's referred to as impulse. So impulse of a force is defined as the product of that force and the time for which the force is acting. For example, consider a there is the ground, there is a ball, a basketball, for example, falling towards the ground. There is that particular instant when the ball just makes contact with the ground, but it is still in motion. It just makes contact with the ground. If at this point we start timing, we will find that the ball will start to lose shape, but it's still moving. And then at some point it's going to stop moving downwards and then start bouncing backwards, upwards, until at a certain time it just leaves the ground. Remember here, the ball is just about to hit the ground. Here it is in contact with the ground and it has momentarily come to rest. And then here it just leaves the ground on its way upwards. For example, let's just assume that it hit the ground with a speed of 20 meters per second and it bounces with a speed of 15 meters per second upwards. This is the initial velocity with which it hits the ground. This is the final velocity with which it leaves the ground. And this is the time for which the ball is in contact with the ground, t. If we were to plot a graph of how the force acting on the ball changes with the time, we'll find that at this particular point, the force acting on the ball is 0. But at this point where the velocity is momentarily 0, that is where the force acting on it is maximum. And then that force reduces to 0 at this particular point. So this is how the force which is acting on the ball varies with the time. If you can get the area, this area, it's going to represent the impulse of this force on the ball, or a physical quantity which we call impulse. After all, when we multiply force by time, because that is how we get the area of a rectangle, for example, width times the length, then we are multiplying force times time, and force times time is impulse. So the area under a force time graph always gives you impulse of that force on that object, and it represents the change in momentum of that object. We shall look at questions of this nature later on. Let's continue and see what emanates from this particular equation. So the first thing is that we can get impulse, which is the product of the force and the time, and we can get the impulse momentum relationship. By getting the impulse of the force on the object, then we are getting the change in momentum of that particular object. Or when we get the change in momentum of the object, we are getting the impulse of that force on the object. So there is that physical quantity that we can discuss. It's referred to as impulse. And if this area is a regular one, like for example, you can be told that the force could be a horizontal line like that, then it's just a matter of multiplying this force by this time and we get the change in momentum, or we get the impulse of the force. When we look at this equation, you find that the left-hand side has got the unit Newton seconds, because it is newtons times seconds. The right hand side is change in momentum, and it will simply be kilograms meter per second. It is at this point where now we see how the unit kilograms meter per second can also be equal to the Newton seconds. And when we say that the SI unit of momentum is kilograms meter per second, it is the same as the Newton seconds. So I've been able to show you that. And that one is very important. Let's look at something else, and this is about the definition of force. First of all, the left-hand side is the resultant force. The right-hand side is the rate of change of momentum. is the rate of change of momentum, is change in momentum divided by time. It is from this that we get the definition of force. At this point, we would like to move away from the definition of force as either a push or a pull and now adapt the correct definition of force. Force is defined as a rate of change of momentum. Force is defined as rate of change of momentum. And the equation which stems from the definition of force is F is equal to ma. Remember, for every physical quantity in physics, the moment we define a physical quantity, we are supposed to give an equation which stems from that definition. This is not possible when we stick to the definition of force as either a push or a pull. It's not possible to come up with an equation which links a push and a pull on that object. But when we define force as the rate of change of momentum, then the equation which stems from that definition is F is equals to ma. Then we can say that the SI unit of force is newtons. The SI unit of force is newtons. And we can define the newton as 1 kilogram multiplied by 1 meter per second squared. Let me repeat this because it's very, very important. We can define 1 newton or the newton. We can define the newton as the force or as the resultant force which produces an acceleration of 1 meter per second squared when it acts on an object of 1 kilogram. Or we can say when a resultant force of 1 newton acts on an object of mass 1 kilogram, it produces an acceleration of 1 meter per second squared. This is referred to as definition of units. So that is how the newton is defined. 1 newton is defined as the force which produces an acceleration of 1 meter per second squared when it acts on an object of 1 kg. And those are some of the things or some of the physical quantities which emanate from Newton's second law of motion. In the next video, we will go through problem solving as far as Newton's second law of motion is concerned, because it's a very important law. We'll start with very simple questions as we go to more complicated questions. See you in the next video.